Swayam Prabha. Digital India. Educated India.
So now we are going to discuss another interesting distribution, which is uniform distribution. This is one of the very simple type of distributions. Now here on the right hand side, you can see the diagram of a typical uniform distribution. In uniform distribution, a value has the same probability of occurrence between the smallest and the largest value. So here, the smallest value of x is a and the largest value is b. And the distribution, if we say uniform, that means the line which you see parallel to the x-axis, that indicates the probabilities. So this line is a straight line parallel to the x-axis, and that means its height is same from point A to point B. What does it mean? It means that the probabilities are exactly same whatever the x is, starting from A to B. All the probabilities are exactly same, and hence this is known as uniform distribution. The probability density function of this distribution also looks very simple. This is simply fx is 1 by b minus a. So b minus a in a way is the distance between b and a to b or b to a, whatever you say. So 1 upon b minus a is the PDF, that is probability density function. So it is 1 upon b minus a, while x varying from a to b, that is the domain. Outside that domain, the value is 0. So it is from here to there. There is another diagram at the bottom. Suppose we are interested to know the probability that x takes values between c to d. So c to d, this is c and here it is d. So the value of x is c and at this point it is d. Within this range from c to d, what is the probability that x value will take between c to d? So what we should do? We take this distribution function fx dx and we integrate from c to d. So this is 1 upon b minus a, that is fx, and we integrate dx over c to d, and that becomes simply d minus c by b minus a. So that is the probability that the x variable is going to take values between c to d. So this is extremely simple type of distributions, and there are some applications that we also will see. The mean of the uniform distribution, if we want to find out the value of mean, which is mu, we have to take this x fx dx. This we have already done earlier, that y fx dx has to be multiplied by x, and then we have what the entire limit, that is the values that x can take. Theoretically it can take from minus infinity to plus infinity. In this case, this is minus infinity means basically a, and the other extreme value is b. So you have to take this x fx dx and integrate between a to b. So it will be 1 upon x dx, and this part is basically its probability density function. So if we integrate it, then we get a value 1 upon b minus a, and x dx integration gives x squared by 2, and the limits are a and b. So if we substitute x square, x value by b and then by a, ultimately we will arrive at this value a plus b by 2. So the mean of uniform distribution ultimately appears to be so simple, a plus b by 2. And the variance also can be proved to be b minus a by 12, b minus a whole square by 12. This is what we are not going to derive. That derivation is a bit lengthy, so we are trying to avoid that. So just remember that mean is always a plus b by 2, and variance is b minus a whole square by 12. Next, we take an example, and with the example, the understanding will be more clear. So the example is what? Now let us say a 31.8 millimeter rotor is running at a speed of 80,000 RPM. Okay, so those who are familiar with the the spinning technology, they understand what is rotor is. If in case you do not know what is rotor or what is rotor spinning, then you have to seek the help of your teachers or your seniors. They can explain what actually a rotor is. So that simple understanding of the rotor spinning machine should be known. Here a trash particle enters the rotor chamber. What is the probability that it will fall on the yarn formation zone, which is 5 millimeter in length? So the rotor is a device by which we assemble the fibers and then twist into it to make a yarn. Now, the process of rotor spinning should be little known to you. Otherwise, it is I should say that it may be a little difficult to understand where the trash particle is going to fall and why it is going to fall there. Anyway, now within the rotor is basically a kind of you can say it's a conical container, and within this container we are actually injecting the separated fibers, and as the fibers are injected inside the container, which is rotor, some trash particles, especially when we feed cotton fibers, can also be there. They can also enter the rotor chamber, and once they enter, they can settle anywhere. So within the rotor, the trash particle can fall anywhere with equal probability. So rotor is basically a device. If I take a cross-sectional view, it will look like this, and there is a channel through which we feed fibers, and a typical trash can fall anywhere. This is the circumference of the rotor, so it can fall from anywhere, starting from here to there. Whatever is the circumference of the rotor, that is available to the trash particle for depositions. So that is what is the rotor will look like. So we have drawn that if I open it up, so we will say that the one end of the rotor, so this is the A end and here is the B end, and A and B are so close to each other. So A is here and we start measuring along the right hand side, and at the point B, which is here, this point B is here. So from A to B, the distance is 100 mm. How? Because rotor circumference is pi into 31.8, which is equal to 100 mm. Therefore, A to B, so B minus A, you can say this is 100 mm. So probability that a trash will fall on any point in the rotor is exactly same. So it will be 1 upon B minus A. That means 1 upon 100 minus 0. It is 1 upon 100, and therefore it is 0.01. That is the probability that it will fall anyway. It can fall here, it can fall there, it can fall here with equal probability. We do not know where it is going to fall, but we are certain that it is going to fall inside always. That probability is 100%. But where it is exactly going to fall, we do not know in advance. It can fall anywhere within the rotor. So probability that it will fall on the yarn formation zone. The yarn forms within the rotor, and let us say the yarn formation zone length is how much? It is just 5 mm. So what happens that within this rotor, the yarn actually fills up. We call this is the yarn formation zone, which is 5 mm. So what is the probability that the trash particle, which is suppose moving this side and going to land inside the rotor, what is the probability is going to fall within these 5 mm? As the rotor rotates, this particular the yarn inside the rotor also rotates along with the rotor, also at a very high speed. So what is the probability that this trash particle is going to land exactly here? So that probability, that means in the look at the diagram, then the C to D, we say that is my yarn formation point. So let us say this is my C point and this is my D point. This is C and this is D. So CD is how much? CD is just exactly 5 mm. That means in this diagram where we have drawn the probability density function and the uniform distribution, we can say here is a place C to D at a particular instant, which is exactly equal to 5 mm. So what is the probability is going to fall there? The probability of X being between C to D will be D minus C by B minus A. So 5 minus 0 by 100, it is going to be 5 by 100. That probability will be 0.05. So this is the probability that a trash particle which is entering the rotor chamber is going to fall on the yarn formation point, which is 5 mm in terms of its length, will be 5 by 100 or 0.05. Now sometimes if the trash particle is big, it can lead to breakage of the yarn. If the particle is very small, it may not be able to disturb the spinning process, but if the particle happens to be big in size, then it can disturb the smooth spinning process and it can lead to breakage. Anyway, so that is the consequence of trash particle getting inside the rotor and disturbing the spinning process. However, the probability of the particle falling exactly in between C and D point or at the yarn formation point is 0.05. This is how we can calculate. Another problem we are going to discuss now. Now here is again another uniform distribution we have drawn, and what it says, suppose X is uniformly distributed over minus beta to plus beta. So here is plus beta point exactly here, and minus beta is somewhere here, where beta is greater than 0. So beta may be 2, maybe 3, maybe 1, maybe whatever it is. Determine beta so that px greater than 1 is 1 by 3 is satisfied. So this is given. Probability that x will be more than 1 is 1/3. This is what is given. So for what value of beta this is going to be satisfied? That is what the question is. So how to go about it? Solution procedure is it's going to start. First of all, we have to know what is the probability density function of x in this particular case. Because it is uniform distribution, so we know that the PDF is simply 1 upon b minus a if you look back the theory part. So here b is beta and a is minus beta. Therefore, PDF of x is going to be 1 upon beta minus beta. So it will be 1 upon 2 beta. Next is probability x greater than 1. If we try to find out, the rule is that density function has to be integrated over the limit. What is the limit? We have to start greater than 1. This would be greater than equal to 1. So from 1 to beta, we have to integrate this density function fx dx. So we write 1 up integration 1 to beta, and what is fx? 1 upon 2 beta. We write 1 upon 2 beta dx. Beta is constant, so we take 1 upon 2 beta out. So what is left within the integration is simply dx. Integration of dx is x, and the limit is 1 to beta. So we arrive at this particular value, which is beta minus 1 by 2 beta. So that is the probability that x is going to take a value greater than equal to 1. So this value has been given. That means beta minus 1 by 2 beta is going to be 1 upon 3. That is given. So once you have this, now the job is very simple. We have to find out what is the value of beta. So we get from here, by solving this, we get beta equal to 3. That is what the value of beta is. So we have solved 2 problems. Now we move on to the another distribution, which is exponential distribution. So there could be some situations in textiles where exponential distribution may be applicable. Exponential distribution looks like this. You look at the curve, it is starting at 0, the value is very high, it's gradually falling, and it follows the exponential law. So exponential distribution is a right skewed distribution, and from 0 to infinity. So starts at 0 and goes up to infinity. The PDF of exponential distribution fx is alpha e to the power minus alpha x, where x is greater than 0. And it will be 0 elsewhere. Total probability, that is the area under the curve, basically means that I have to integrate this curve from 0 to infinity fx dx, and that value should be equal to 1. So total area under the curve is going to be, and that is the total probability, which is always 1. The interesting point is that the mean value of exponential distribution is 1 upon alpha. So alpha is a parameter of exponential distribution. So you can say the exponential distribution can be described by only one parameter. It's not like normal distribution where you need two parameters to describe the distribution, and in that case it was mu and sigma of the normal distributions. But for exponential distribution, it is only alpha, and the relationship between alpha and mean is 1 upon alpha, and standard deviation is 1 upon alpha square. So if I know alpha, we can find out whatever is the mean of the exponential distribution and what is the standard deviations. And from there we can also find out what is the CV percentage. All of them will be known to us, provided we know the value of the parameter alpha. But if I know mean, then I know what is alpha, because mu and alpha are connected by this equation. Where does it used? One is, it is used in queuing theory. Like length of time between successive arrivals of customers in a bank. Length of time between successive end breaks on any machine. It could be ring spinning machine, it could be rotor spinning machine, it could be winding machines. Length of time between successive stoppages of loom in a loom shed. These are few examples where exponential distributions can be used. Many times you will be interested to know the cumulative exponential probabilities, that is capital Fx, not small fx. There is a distinction between these two. Small fx is the probability density functions, and capital Fx means cumulative distribution functions. So capital Fx basically will mean probability that the variable x takes values less than equal to small x. It is always less than equal to small x. That is what is known as, that is what is capital Fx. So that basically means if I want to know this value, I need to integrate fx dx from 0 to x. So if I do that, I write the distribution density function alpha to the power minus alpha x, then we go for integration and we will end up with this. If we go step by step, this is a very simple integration. We end up with this 1 minus e to the power minus alpha x. So probability that x is going to take values less than equal to x equal to 1 minus e to the power minus alpha x. Similarly, we can again show that fs, if I define, is that it is the probability greater than equal to x. In that case, it will be 1 minus px less than equal to small x, and therefore this is going to be the value. That is, this 1 will not be there. So this is how we can find out whether px is greater than x or less than equal to x. Now we will solve the problem. The first problem is an on-job injury in a textile plant occurs every 10 days on an average. Let us say there is a weaving shed where we have 100 looms, and let's say there on an average the data, if we collect throughout the year, that on every 10 days there is going to be some injury of the workers which are there. So what is the probability that the next injury will occur within next 10 days? This is what the first question is. The second is, no injury in the coming 5 days. So injury to injury, that time that we take is a length of time, no, between two events. So injury is an event. So one event to another event, how much time elapses? So time is in terms of days here. Sometimes it could be in terms of second, millisecond, it could be minute, it could be hour, whatever it is. So here is in terms of days, and we need to find it out. So mean is given. So we know the parameter alpha and relationship between parameter alpha and mean. Mean is 1 upon alpha. So that means 10 is equal to 1 upon alpha. Therefore, alpha is 0.1. So the parameter of the distribution is known to us now. What is the value of alpha? So next injury within 10 days will be equal to, that means probability that the event will occur in less than equal to 10 days. So we write directly this formula, 1 minus e to the power minus alpha x. So we basically put the values of alpha, which is 0.1, and number of days is 10, so we write 10, multiply it by 10, and we evaluate this function. We end up with a figure 0.6322. That is the probability. The other one, no injury in 5 days, means 1 minus probability of injury in the next 5 days. So it will be 1 minus p x equal to less than equal to 5. So 1 minus 1 minus to the power minus f. This is the formula. So we substitute the value of x here. The x is now in this case is 5. So multiply this by therefore 5. And it will be e to the power minus 0.5. So they end up with the value 0.6065. From there, we take another example. If on the average 3 trucks arrive per hour to be unloaded at a warehouse, what are the probabilities that the time between the arrivals of successive trucks will be less than 5 minutes or at least 45 minutes? Because depending upon the probabilities, the manager can decide the availability of manpower. For unloading or loading, you need laborers to do the job. So if we know what is the probability and whether the probability is very high or not, accordingly one can think of, or we can make an advanced planning about the manpower availability. That is how it can help. The solution for the problem A is mean arrival time is given. 3 trucks arrive per hour. So arrival rate is 3 per hour. So mean arrival duration is how much? Per truck is 1 upon 3 hour. Next, relationship between mean and the parameter alpha of the exponential distribution. Mean equal to 1 upon alpha. So, and that is what is 1/3. So alpha is 3. So the value of the parameter alpha we can find out. This is 3 in this case. Now the time has been given in terms of this mean has been given in terms of which unit? The unit is hour. So therefore, when we try to calculate the probability that less than 5 minutes, we have to actually change the unit 5 minutes to hour. So 5 minutes is equal to 1 by 12 hour. We have to be very careful about the units. If we take the average in terms of minutes, then everything should be calculated on the basis of minutes. If it is hour, then we have to calculate. We have to make sure that the units are all hour. So this equation is known to us. We use that equation. So probability x less than 5 minutes is equivalent to probability of x less than 1 upon 12 hour, because we have to finally average is given in terms of hour. So write this and just substitute the values now. So alpha is 3, we write 3. X is 1 upon 12, we write 1 upon 12, and we calculate the value. It gives us a figure 0.2211. So that is the probability that the time between the arrival of successive trucks will be less than 5 minutes. So 0.2 is the probability. But we can calculate, if we have on the Excel, if we go there and we choose the right function, exponential function, and we can give different values of x, starting from 5 minutes, 10 minutes, 20 minutes, 40 minutes, 1 hour, or 60 minutes. So for different values of x, we can calculate the probabilities. And then we can plot those probabilities to find out how the probability is changing as the value of x is changing. That also can be done to see where it is coming maximum. Here we have done the calculation because it is done manually, so we have done for only one particular duration of time, which is less than 5 minutes. The another one we have chosen at least 45 minutes. So same equation we have to use. Now the time duration has changed to 45 minutes. So we find out what is the equivalence of this in terms of hour. So 45 minutes means 3 by 4 hour. So you use the same equations. Now here it has to be greater than equal to x, at least 45 minutes. So it should not be less than 45. It should be 45 minutes or more. So the question in this case is not less than 45 minutes. So the formula in this case will be e to the power minus alpha x. It is not 1 minus e to the power minus alpha x. So here we substitute alpha by 3 by 4. Value of mean is known already 3. We get it e to the power minus 9 by 4, and this will give you a probability which is 0.105. So this is how we can calculate the probabilities. So now with this we have discussed 3 different distributions which are quite popular, and there are many more distributions. We cannot cover all the distribution in this particular course. So few distributions which are important for us, especially for textile and apparel engineering students, those distributions we have covered now. And you must solve problems, as I've already mentioned earlier, that you can get any textbooks or even from the internet sites. You will get many problems which are already solved there, or problems are given and one can solve it. So as you keep solving it, the skill will develop and you will be able to solve any unknown problem very fast. Okay, with this we close this particular discussion on continuous distribution. Thank you.